Okay, so now we spent a lot of time on the fundamental concepts of calculus. So now we're going to show you how to use it in problems. Okay, so we'll do a few problems. Usually I'll try to solve and do problems on the second half of the Thursday lecture, because we've sort of built up all the ideas, and then we'll do a little bit of practice. Let's see. Okay, let's see. All right, so there's two kinds of problems I list up here, right? There's plug and chug, constant acceleration kinematics, and then this is where it gets tricky. So first let's do one of these. Let's do a plug and chug, and then we'll do a trickier one. So this example is I throw a chalk down in disgust, like this. Ah, so mad. Okay, so throw chalk at 2 meters per second. Was that 2 meters per second? It's per second from the origin at t equals 0. So it's actually important. Sometimes people get this mixed up in problems because they think it has to be hard. So what we're saying is this chalk was released, coordinate system, let's make down positive because it makes life easier, released at the origin, and it had some initial velocity, vi equals 2 meters per second. And remember, Galileo said when something is free, it has this constant acceleration. That is, I will tell you, 9.8 meters per second squared. You've probably heard of that number if you've had a little physics. 9.8 meters per second squared is the acceleration at which things fall. Okay? So sometimes people will overthink it and think, well, how hard is the hand pushing? And is the hand accelerating it to be different from 9.8? The answer is yes, that was to get the problem started. But in almost every problem, the problem is about once the object leaves the hand, and it's just going at 9.8 meters per second squared. Okay? So we're not writing problems for plug and chug. It's usually, if it's not clear, if you think, I guess they mean that it's a free particle, yes, we mean it's a free particle. So we don't put at the end of every problem, by the way, the chalk is released from the hand, therefore it's accelerating at 9.8 meters per second squared. Right? That's always kind of the case. Unless we say explicitly, it is accelerating at something else. Okay? So you're only solving the problem after it's left the hand, and it's already traveling at 2 meters per second, and it's accelerating at 9.8 meters per second squared. So the question is, where is it at 1/4 second later, 0.25 seconds? Where is it? So you got to say, well, let me think. Where could it be? I don't know. Which equation do I use? Go to the back of the book, find the equations. Oops, got a little excited. Sorry, okay. So you say, well, this is acceleration for a certain time. So it's just the standard kinematics equation. X final equals x initial plus v initial t plus 1/2 at squared. And the problem like this, even though it's plug and chug, you're just going to put numbers from the problem into this equation. You do have to be able to know a little bit what's going on. You have to say, what is xi? It's 0 because we started at the origin. So you got to be able to do that. Just drop it like it's not right there. And then vit, what is vi? That's what they gave us, right? I threw it at 2 meters per second. That means it was going 2 meters per second when I released it. It might speed up after that, but 2 meters per second. And what is t? I'm not saying delta t. Well, that's because I released it at t equals 0, and I want it 0.25 seconds later. So if you want to be real specific, you'd say t initial equals 0, t final is 0.25, delta t is 0.25. Right? We don't get that specific often when we're solving problems, or if we're posting a solution for you. We will be sort of into this enough to just say, put 0.25 there. Okay, we might not always, write out TITF, delta T, XI, XF, delta X. Right? So that's the kind of things, even for a plug and chug, you need to be able to kind of start getting the hang of. Right? So 2 meters per second, 0.25 plus 1/2, and then A, I told you, is 9.8 meters per second squared. Right? And then T squared, 0.25 squared. Right? That's your delta T squared. So that's the sense in which this is a plug and chug constant acceleration problem. Is we gave you all the numbers you need, 2 and 0.25, and 0 and 0, or 0 here. Then you plug it in, and blah, blah, blah. You get xf equals 0.81 meters. And you're done. That's how far down it went. Now, we have ways of making plug and chug problems hard, right? Just because that's, we just sit around all day and say, oh, they'll really hate this one. Let's do this, okay? But a good follow-up, what if I threw it up? Same question, what if I threw up instead of down? Right? What would you do? What would you change? You'd say, well, I still want to know where it's going. And they didn't say so, but I would assume I still threw it from the origin at time equals 0. Right? If we say all you do is throw it up instead of down, you would assume all these are the same, right? So you'd say, okay, xi, that's going to be 0, right, because it started at the origin. And you'd put a -2 here. Right? Because now I've defined down as positive. If I throw it up is negative. Plus 1/2 9.8 times 0.25 squared. All right, so y'all think about that for a second while I check the text log here. Let's see, I've really got to turn my speaker on. Are we allowed to text you questions outside of class? Certainly, I may or may not answer them right away. What is the significant figure accuracy that the answer needs to be to? So every problem in the homework is set at plus or minus 5%. So that's pretty low accuracy. So just hit it within 5%. I thought it was negative 9.8. Why isn't it negative? Yes. This is how even plug and chug can get hard, is because I defined down as positive. I can make down positive if I want. In physics, we can make any direction positive. Down is positive, therefore this initial velocity was positive and g was positive. Down is still positive, but we threw it up. So the initial velocity is negative, but down is still positive. Right? The only thing I changed is what if I threw up, which was a poor choice of words. So if you plug in and solve that, what are you going to get? X equals minus 0.194 meters. This negative ends up being bigger than that positive. You get a negative number. And then you panic. Can position be negative? Is it like a tesseract or something? No, position can be negative. It just means you're on the other side of the origin. Right? If you throw it up, let's see what happens. Up and down and crash. Right? So for part of the time, it was above the origin. Okay, here we go. Let's see. Why doesn't the sound acceleration change? Oh, that's a good question. Okay. Oh, Lord. Here we go. Oh, my God. Okay. Where did the 1/2 ATT come from? So this is the kinematics equation that we derived both with calculus and graphically. And now I'm just using it. Okay, that's a standard kinematics equation. Okay. Why doesn't the sign of the acceleration change? The acceleration direction never changes. I said down is positive, therefore g is positive. It'll always be positive. When something is moving up, it can be accelerating down. All right. If something is moving up, its acceleration is down if it's slowing down. So when I do this, here we go, let's make it dramatic. This is going to leave my hand. And between the time it leaves my hand and hits the table, or hits the floor, the table, okay, oh, sorry, the acceleration was down the whole time. The only time the acceleration was up is when I was throwing it, right? But we're not talking about that part. We're only talking about the part when it's free, right? That's the free part. We'll never really solve the part when something is pushing it this week, except for one problem. But I was going to do the example too. Do I always define down as positive? No, it's totally up to you. Either way is positive. Why is the A still 9.8 when you throw it up, even though you put force behind it to make it go up? Excellent question. I put force behind it to make it go up, but you're only solving it for after it leaves my hand. Once it leaves my hand, it's only experiencing gravity down. That's why I was trying to specify the free part. You're not solving for when my hand pushed it. All my hand is doing is giving it an initial velocity. You're just solving it when it's away from my hand, and then all it can possibly do is have acceleration down. Why do I make 9.8 negative? Yeah, right, because it's down, and I said down was positive. Right? Okay, so it's tricky, right? That's the plug and chug, right? See how tricky plug and chug can get? Oh, they have to even tell you how to make it even worse. But let's make it worse. So if you solve this for negative, and you get negative 0.194, let's think about the motion. When you throw it up, it goes up and down, right? So we're saying at 0.25, it's at negative 0.194. But was it going on the way up or was it going on the way down? Which one was it? What do you think? There's no way to know just by looking at it, unless your mind is like a really fast calculator. So how are you going to know? Is it on the way up or is it on the way down? Put it in your graphical calculator. Yeah, I know. You have a graphical calculator. The other way would be to think, well, what's the difference between going up and going down? Is the velocity, right? So if we said is it on the way up or on the way down, what you'd want to say is, let's see, up or down, is you'd think, well, I want to deal with the velocity. I want to know is it positive or negative? So you go to your other kinematics equation. I should have left them up, right? There's that one, and then there's this one. V final equals V initial plus AT. That was the other fundamental kinematics equation. You'd say, okay, let's see if I can get all the signs right. I gave it initial velocity up. That's negative 2 meters per second. Plus, and I'm treating down as positive, 9.8 t. And t is 0.25. So is that number going to be positive or negative? Let's see, 10, quarter of 10, 2.5. I think it's going to be positive. Yeah, it's positive. It's barely positive. Right? This is, if this were 10, it'd be 2.5, and 2.5 is bigger than negative 2. The answer is 0.45 meters per second. So the answer is, it's going up, it's going down. Sorry. I can't even get it right. So is it going up or is it going down? It's going down. Because we got a positive number, and we define down as positive. Right? So we caught it here, right there, going up or down. See how horrible a plug and chug can be? That was all plug and chug, right? Well, we only used two equations. We use VF equals VI plus AT, and we use this. Okay? There'll be some true plug and chug where you don't have to do all these tricky things. Mm-hmm.
I'm still a little confused why the 2 is negative if, like, sure you threw it up, but it's still, like, after it's
right.
going down.
Yes. You're thinking of what we're solving for. We solve for a velocity down. This is the initial. I gave it an initial up. So that's positive, or negative, because I gave it an initial up. Mm-hmm.
Can you draw the x versus time graph?
Yes, that's a good idea. Let's draw the x versus time graph for this problem. Now, hold on to your hats, okay? Plus x, I'm drawing up on this graph, but in reality, positive x is down. Are you ready? I don't even know if I can do this. Let's see. So it starts at the origin, right? And we gave it initial, which one are we doing? Up or down? Throwing like this or throwing it down like this? Okay. Let's do the original then. No, let's throw it up because it's more complicated. Okay, we threw it up. We gave it an initial negative velocity because we threw it up. So the initial slope is going to be negative. But then gravity is going to turn the velocity and make it positive because it's pushing it down. So it will look, position would look like this. Except crash, it would hit the ground like that. So that would be the position time curve. And you say, wait a minute, that's not really how it moves. It doesn't go down and up, it goes up and down. But that's because I made this down positive and I plotted it up positive. So all these switch arounds you got to get comfortable with. Every problem won't require this much switching around. It's also up to you. You could solve the problem and make this up positive. The problem didn't tell you what to do. You can always make up positive if it makes you feel better. Right? I just made up down positive just to make it more fun, right? To make it more instructive. Does an acceleration change based on how far up it goes because of gravity's effect on it? Yes, but don't worry about that. Gravity is constant 9.8 unless you go really, really high. Do we need to use units in all the steps of calculating stuff in the homework to turn in on tests? Let's see. I don't think the graders need to see unit on every step. You're wise to include units a little bit as you go to make sure they're canceling correctly. But I don't think they check something that careful. So the position doesn't cross the origin. Here, oh no, you're right. This isn't the floor. Holy crud, let's see, down. Well, it depends what you mean the origin, right? So here I'm applied, it comes up and it stops back in my hand. This is it landing in my hand. If you consider the floor to be down here, then it would make it to the floor and then it would crash. Right? So I caught it in that one. Okay.